for graphical solutions, we will use the half dimensions. Means if it is 2L in 2L dimension for the plane wall, we will use L as the characteristic length. Similarly, if diameter is the total dimension of this cylinder, we will use R naught as the characteristic length for calculating Biot number, H R naught by K. Similarly for sphere, H R naught by K, and then that is dimensionless heat transfer coefficient or Biot number, right? Next is the dimensionless time, which is nothing but Fourier number, alpha t divided by characteristic length L square for plane wall. For cylinder, it will be alpha t divided by R naught square. Similarly for sphere, alpha t divided by R naught square. So if we know these parameters, then we will be able to use the graphical or tabular solution easily. So here I am going to present only the graphical solution. Tabular solution you can learn or see in any textbook. Okay, so let's begin with the plane wall. Suppose we are interested in finding the temperature at the center plane. So there were the two scientists who gave these charts, Heisler. These two charts were given by Heisler in 1947, and the third chart, which is to find the heat transfer at any time, given by the Grover. All right, so by using this chart, we can find the temperature at the center plane. Suppose we want to find that after 8 minutes, what is the temperature at the center plane. So for that particular time, we find this Fourier number, alpha t by L square, and corresponding to that Fourier number, we will go for the reciprocal of Biot number. Let's say 26 is the full non-dimensional time, and 4 is the reciprocal of this Biot number. So corresponding to that, what is the y-axis value? So that will give you the center line non-dimensional temperature. So it is function of Fourier number. This is plotted as a Fourier number and 1 by Biot number, and this is non-dimensional temperature. So all these red lines here represent the 1 by Biot number. All right. Similarly, if we want to find that at a particular location from the center plane, what is the temperature, then it is plotted in the second graph. On the y-axis, temperature at particular x and particular time. Here T naught is center plane, means 0 location and particular time. So Tx minus T infinity upon Ti is initial temperature, minus T infinity is a function of non-dimensional position as well as reciprocal of Biot number. So particular this reciprocal of Biot number, and then that, let's say we want to find at the outside surface, and for this particular Biot number for the outside surface, this will be the line x by L equal to 1, means we are at the outside surface, right? So for that particular Biot number, for that particular distance, what is this theta value? So we have to plug in there and we can find the temperature at that particular location. Moreover, if we want that what is the heat transfer, what is the energy transfer from this particular time to that final time, also from initially to final, so we can find from the Grover chart. Means we have to first find there is no place to write. So let's say we want to find the heat transfer at particular time. So first we will find the Biot number square times Fourier number, which is plotted on the x-axis here. Okay, and Biot number, so for that particular axis and Biot number, let's say we are here, and that corresponding y value we will give us the q by q max. And what is q max here? The question comes, q by q max. Let's say some value will come, which is function of this Biot number square, Fourier number, and Biot number. What is q max? Q max is the heat transfer in joules of the body. Let's say body is having mass m, cp, thermal conductivity, specific heat, times the what is the maximum heat transfer it can have from initially to the final ambient temperature. Okay, means in which it is going to give the heat or take the heat that from surrounding fluid. So let's say initially it is having high temperature Ti, and finally it is going to reduce the temperature to T infinity. So that is going to the maximum heat transfer, which is depending on the rho times volume times P times Ti minus T infinity. Alright, so like this we can find the heat transfer in joules at any particular time from the body for the plane wall. I explained for the case of plane wall. Similarly, for long cylinder, the center plane temperature at any time is a function of, again, Fourier number plotted on the x-axis and one by Biot number, as these pink lines shown here. So we can find this value, center line temperature, from this relation from first graph. Okay, for finding the temperature at particular location, let's say at distance r from the center, particular time t minus T infinity upon Ti minus T infinity is a function of that non-dimensional location, means x by L. Sorry, it is not x by L here. It is actually r by radius, r naught. Okay, it is plotted here, and 1 by Biot number plotted on the x-axis. And if we want to find the heat transfer at particular time t with respect to the maximum heat transfer it can have during the process, suppose the body is cooling from initial temperature Ti to the ambient temperature T infinity. Okay, T infinity means final temperature at the end of the process. After that it is not going to reduce any temperature, or it will not going to transfer any heat. So in between, if we want to find at particular time t, what is the heat transfer up to this process, so that can be find, and that can be find as q, and total heat transfer from Ti to final ambient temperature is q max, is function of Biot number square times Fourier number and Biot number, and we can find this from third graph. Similarly, same relations valid for sphere also. Alright, now we have looked upon that how to find center plane temperature in any particular location, and the total heat transfer for particular time. Notice that all these graphs are valid for Fourier number greater than 0.2, in which only one term solution is there for this equation, right? Okay, so one term solution is plotted in these all graphs. So while using these graphs, you have to be very careful that Biot number should be greater than 0.1 and Fourier number should be greater than 0.2. That is the thing I want to emphasize. I wanted to emphasize. Now we will try to move forward. So now we have looked upon that how to find these temperatures and how to use this Heisler and Grober charts. We are going to solve a numerical problem to implement this analysis. This is a classical problem I have taken from the Incropera book of the heat transfer. Okay, so what this problem says: consider a steel pipeline that is 1 meter in diameter and has wall thickness of 40 mm. The pipe is heavily insulated on its outside, and before the initiation of the flow, the walls of the pipe are at uniform temperature of 20 degrees Celsius. What it says, let's draw this diagram for this first. There is steel pipeline, right? It is having some thickness. This is the center of the pipe. Okay, and they are saying it is heavily insulated from its outside surface, right? It is heavily insulated from outside surface, and its thickness is 40 mm and diameter, they're not saying anything, so let us take it as inner diameter 1 meter. All right, and the pipe is at uniform temperature of minus 20 degrees Celsius. It is minus 20 degrees Celsius actually. Some mistake is there. So the pipe is initially at minus 20 degrees Celsius before the initiation of the flow. Okay, I think that problem is taken from some cold countries like Netherlands. Okay, so and suddenly the hot oil is started to flow inside this pipe, right, at temperature of oil at 60 degree Celsius, which is creating a convection condition on the inside surface corresponding to heat transfer coefficient as 500 watt per meter square Kelvin. So it is asking that find the Biot number and Fourier number 8 minutes after the initiation of the flow.